Hi, I'm Brian Freer, tutoring high school physics. Today's topic, intensity, beats, and resonance with sound. Intensity is, well, it's a measure of how intense sound is. Says pretty much what it is. It's described as the power of the sound divided by the area over which it is dispersed. The useful formula to know for this is that the area of a sphere, the surface area, is equivalent to 4 pi r squared. This is because sound typically is dispersed in a sphere from its source. So let's say that we have some sound is being emitted with a power of 40 pi watts. And we are standing 1 meter away from the source. So then we're going to throw in the surface area of a sphere formula, 1 meter as our radius. What is the intensity of this particular sound? Well, I've set up the equation. If you run it through, you'll end up finding the intensity is 10 watts per meter squared. If you have an intensity for sound, you can convert it into a decibel measure. The formula for decibels is beta, representing our decibels, equals 10 times the log of our intensity divided by the threshold of hearing intensity, which is 10 to the negative 12 watts per meter squared. So let's convert this into decibels. Beta equals 10 times the log of 10 divided by 10 to the negative 12, and these are all watts per meter squared. You notice that we're going to come out with no units for this one because we have watts per meter squared on both the top and the bottom. Beta equals 10 times the log of 10 to the 13, and so that's just going to give us 13, so 10 times 13 gives us 130 decibels. Alright, so that's it for intensity. Next up, beats. When you have two different sound sources, and they're playing at different frequencies, you're going to hear beats. If you've ever tuned an instrument, you've heard these before. To find the frequency of a beat, all you have to do is find the difference between two frequencies. So say that you're tuning at 440 hertz, and you hear beats of 5 hertz, because you have extraordinarily acute and numerical hearing senses that let you detect exactly what the beat frequency is. So, what is the frequency of your instrument? Well, it's actually one of two things, because as you see we're taking the absolute value, it's only the difference. We're going to be able to, so our instrument is going to be either at 445 hertz, 440 plus 5, or 435 hertz, 440 minus 5. Because there's a difference of 5 beats. Next up, resonance. If you're playing a sound into a closed tube, such as this one, it's going to hit the end of the tube, and just like a string attached to a wall, the wave is going to reflect, and so you can generate a standing wave. There is one catch to this. If you're creating a sound in a closed tube, you can only create resonance, a standing wave, with odd numbers of harmonics. So you can have the first harmonic and the third harmonic, but not the second harmonic. You can use these equations, however, to calculate the frequency and the wavelength of that particular harmonic. So let's try to calculate the first harmonic for a wave that has a tube with a length of 4 meters, and the wave has a speed of 2 meters per second. So a wavelength is 4 times the length of the tube divided by the particular harmonic that we're trying to get. So this is the first harmonic, so we can just get rid of the n, and we have 4L. So 4 times 4 meters gives us 16 meters in terms of wavelength. Wow, that's a pretty big wave. Next up, let's find the frequency. Frequency sub 1 equals, so this is just going to be 1, and we have velocity of 2 meters per second over 2 times our length, which is 4 meters, so then that's 8 on the bottom. 2 divided by 8 is going to be 1 over 4, or 0.25, and that's going to be in hertz. Interestingly enough, if you have an open tube, the sound will also reflect and generate a standing wave. With this, all harmonics are possible, and you use these equations to calculate them. So let's take the exact same wave with a tube of length 4 meters and velocity of 2 meters per second and calculate its wavelength and frequency. So wavelength this time is 2L times n, so 2 times our length of 4 meters divided by n, which is just 1 because we're calculating the first harmonic, and we get 8 meters for a wavelength. Notice that this is different from a closed tube resonance. Alright, now let's also calculate the frequency. So frequency 1 equals, that's just going to be 1. Velocity is 2 meters per second over 2 times our length of 4 meters. This is going to be the same, however, and we get 0.25 hertz. However, remember that with this one, all harmonics are possible. So you could find the frequency of the second harmonic here, but not over there. Alright, to recap. You can measure the intensity of sound by dividing the power of sound by the surface area over which it is dispersed. Sound tends to be emitted in a sphere, so it's useful to remember the surface area of a sphere is 4 pi r squared, where r is the radius. You can convert an intensity into decibels by taking 10, multiplying it by the log of the ratio of the intensity you want by the threshold of hearing intensity, which is 10 to the negative 12 watts per meter squared. You can hear beat frequencies when two sounds with different frequencies are played. To find the beat frequency, simply find the difference between the two sound frequencies. When playing a sound into a closed tube, you can create a standing wave when the sound wave reflects off the closed end of the tube. We can use the equation to find the wavelength 4 times the length of the tube divided by the n, where n is the nth harmonic that you want. You can also find the frequency of the nth harmonic in that particular closed tube by multiplying n times the velocity of the wave divided by 2 times the length of the tube. However, you can only use odd integer values for n for a closed tube resonance. For an open tube resonance, you can use any value of n, so any nth harmonic can be created, and the equations are for wavelength 2 times length of the tube divided by n for the nth harmonic, and for frequency, it's the exact same, n times the velocity of the wave divided by 2 times the length of the tube. Alright, that's all for now. Again, I'm Brian Greer. See you next time.